Hello, welcome to the University of South Florida Master of Science in Electrical Engineering for Professionals Capstone project for 2014. This will be a comparison of 3C SiC versus silicone for power electronic applications. Project members include Daniel Simons, AJ Patel, and Anna Rampandareth. Our coordinating advisor is Dr. Steven Seau, with our technical advisors as Dr. Farakides and Dr. Hoff. Executive summary. Silicone has been the industry standard due to the reliability, efficiency, and ease of fabrication. Many major technological advances have been made in silicon carbide semiconductors for high field and high power device applications. This project will focus on the cubic form of SiC, commonly known as 3C SiC. Our project objectives include a comprehensive literature search to identify mainstream uses for 3C SiC devices. We'll utilize published characteristics, including material analysis and calculation of key performance factors, to compare 3C SiC and silicone side by side. We'll identify the benefits from the properties exhibited by 3C SiC, create a cubic silicon carbide device model for P-Spice, employ that model within a circuit design, and simulate a power supply using that model. This chart depicts electrical and material properties of silicone versus 3C SiC. I'd like to highlight the increased band gap in 3C SiC, the increased thermal conductivity, and the decrease in the intrinsic carrier concentration. This table shows various other compounds used to make semiconductors. Please take a moment to compare. Some of the benefits based on the previous tables include 10 times the breakdown field of Si, which incur higher switching frequencies, which will in turn equate to smaller sized devices. There's a higher thermal conductivity, which equates to higher operating temperatures. There are majority carrier devices, again equates to faster switching, and there's a lower reverse recovery current, as we'll see in the following slides. Here we see the Schottky barrier diode as a majority carrier device, which gives you faster switching as compared to a p-n junction diode and a fast recovery diode over a given voltage range. On the left we have a physical description of a diode, followed by the electrical description and the ideal diode equation. On the right there's 4 bias characteristics of a silicone and a silicon carbide diode. Notice on the silicon carbide diode there's higher operating temperature range, which will yield higher power efficiency. Here's a great comparison of the reverse recovery waveform between a silicone fast recovery diode and a Schottky barrier SiC diode. Notice on the fast recovery a large negative current swing, and it changes versus temperature. On the right, the negative current swing is not so large, and the temperature variation is negligible, thus making the Schottky barrier diode a better diode for higher power, higher switching devices. Here we show silicone versus silicon carbide on-state resistance. The lower on-state voltage drop for the ideal silicon carbide diode will yield higher power efficiency compared to that of an ideal silicone diode. This is the proposed circuit that we'll utilize to compare silicone and 3C SiC. It is a 100 watt rectifier. We'll perform analysis using the current configuration, then replace D1, D2, D3, and D5 with silicon carbide diodes and perform analysis and compare. At the end of the day, use of silicon carbide components will increase switching frequency, increase operating temperatures, decrease number of components within a circuit, decrease circuit size, decrease cost. Project collaborative and individual responsibilities are as follows. Our project timeline.
The following slides will present information about our team members.
I'm Dan Simons. I received my Bachelor of Science in Electrical Engineering with honors from the University of South Florida in 2007, after which I was commissioned in the United States Navy. I'm currently serving my 16th year of active duty.
I'm Ajay Patel. I have a bachelor's degree with honors in physics and microcomputer electronics from the University of London in the UK. I currently work for General Electric Healthcare as a systems engineer, primarily responsible for the implementation and design of radiology imaging software and systems.
I am Anand Rampadarat, and I am currently a lecturer at the Anton de Kam University of Suriname, located in my home country, Suriname, South America.